Okay, as we continue our series in special topics in BPA, we're going to pick up on this particular presentation that's called Tails of the Tails. And we're going to look at the tails of spatter stains and how we can use those when it comes to interpretation. So the typical disclaimer, I enjoy you visiting and watching these videos, but please remember that you need to find a mentor in order to get competent in BPA. So let's look at this particular section of a wall. There's actually a lot going on here as we look at this area of staining on this wall. There are actually three separate patterns here. We have pattern P, Q, and O. And the way that we differentiate different patterns is there an area of unstained target surface between two areas? And in here, we don't really have that. We have overlapping areas of staining. So for areas of overlapping staining, do we have differences within the features of those areas that are overlapping? And we can see that we have some differences in features, and I've went ahead and labeled them for you as P, Q, and O. But we're not going to break down the individual features within these patterns and try and classify them. But if we would look at the location, size, shape, distribution, and appearance. And we can see some differences here, particularly with O and Q. With O, we've kind of got this curvilinear distribution of circular to elliptical stains, whereas with Q, we have a linear distribution of circular to elliptical stains, and P is just kind of an irregular shaped mess. But what I'd like to focus on is the spatter stains. The spatter stains are the circular to elliptical shaped stains that are actually in all three of those patterns, but primarily in O and Q. But here's we look a little closer at O. We're not going to break them down too terribly much because our typical breakdown would be the size and the shape and the distribution within those shapes. These here are going to be about 7 millimeters down to about 1 to 2 millimeters. We don't really have many that are much smaller than that. But what I'd like to focus in on is what we can learn from the tails. And we often don't spend a lot of time talking about the tails of spatter stains. We know they're there. But I'm going to encourage you to look a little closer at the tails because I think that this is an area that we might be missing some pretty critical information. So the typical approach to looking at tails is using the tails to tell you the direction that the droplet was traveling at the time it impacted the target surface. And the tails are on the trailing edge of the droplet travel, so they are pointing in the direction that the droplet was going, not where it was coming from, but where it was going. So you can see the red arrows are showing that within this particular pattern for G, these stains were all generally going in an upper right to lower left directionality. Now they're not parallel, we have some arching going on, and that's going to help us in our classification. But these are all essentially going upper right down to the lower left based on the tails. And that's typically where we stop when it comes to evaluation of the tails. And I'm going to encourage you to look a little more into that. But before we look at the tails of spatter stains, I'm going to take a little bit of a deviation. We're going to look at the edge characteristics of drip stains, particularly this particular publication that came out in 2005, where these researchers were trying to determine if you could look at the edge characteristics of drip stains to determine the impact velocity from them. And we've seen this within our basic courses or the introductory courses, that if we have the same volume of drop, and as the drop falls further and further, the edges change, particularly if we're looking at a generally smooth surface, such as cardboard. From low heights, the edges are going to be relatively smooth. We're going to have a round shaped stain. But as we get higher up, the edges become scalloped, which is kind of this wavy appearance to them. And then we'll have these spines that start extending out from them as we get higher and higher. And what these researchers did is they started counting the number of spines and the number of scallops. And what they found came with the spines is that the greater degree of splashing, or as the number of spines increased, that was an indication of higher velocity, that the droplet was moving faster when it struck the target surface. Now they were trying to connect that to dropping height, but what the takeaway here is that splashing is an indication that these droplets were moving faster at the time of impact. We have another study that supports that, and this one is looking a little more in depth into the concept of fluid dynamics. This paper came out in 2019. They're looking at the region of origin for bloodstain patterns containing spatter stains. And there's a lot of information within this particular one, particularly when it comes to the concepts of fluid dynamics. And you can kind of see this on the chart on the right-hand side. And this particular, they're graphing the Weber numbers as well as the Reynolds numbers, and they are linking that to what happens to the droplet when it impacts the surface. In certain conditions, you're going to have smooth edges. In other conditions, you're going to get a wavy edge, which is going to be a scallop shape to that. And in others, you're going to get an indication of splash. And the red arrows show the differences in the tails. Here at the bottom red arrow, we've got a single tail that's extending out. And in the upper red arrow, we have kind of more of a jagged or a splash shape appearance when it comes to the tails. And what they said is, for impacts with higher inertia of magnitude comparable to surface tension, the periphery of the stains exhibits deformations such as waves or spines. Okay, well, what does that mean? Just like the previous study, as the droplets strike the surface, the faster they move, it affects the shape of the tail. If it's not moving very fast, then you're going to have virtually no tail at all. Whereas as you increase speed, you may start coming up with a single tail, but as the velocity gets even higher, that single tail breaks into more of a jagged shaped tail. And the jagged shaped tail are those stains that are moving at a higher velocity when they strike the target surface. So let's look at how we can apply this in BPA. Particularly, let's look into area of origin and area convergence determinations. When it comes to stain selection, ideally we are trying to find the stains that had been affected the least by gravity and drag. So we want to find the stains that are moving the fastest when they hit the target surface. So the typical criteria are elliptical shaped stains with well-defined ellipse in the area of 1 to 2, maybe 3 millimeters wide. Some will say get as close to the area of convergence as you can. One paper says look in the upper quadrant or within the pattern if you can. Get them from both sides of a radiating pattern, and those are really, really good. And if you look at the red ovals here, these are the typical stains that a lot of people select when it comes to area of origin and area of convergence determinations. These are nice, well-defined, elliptical shaped stains with edges that you can, with a tail that can tell you the direction. Now the upper one is not one that's going to be used because that is a downward moving stain. But the four lower ones are these are pretty good stains. The ones in the yellow are often ones that we would avoid because it's going to be a bit of a challenge determining the width and the length of these stains because the back ends are pretty jagged. I'm going to encourage you to start looking at those stains when it comes to area of origin determination because those are the stains that are moving the fastest. If we look at the two stains that are on the right-hand side of this slide, you can see that tail isn't a single tail coming off. It is a jagged tail. And there's multiple spines and streaks that are extending outward. That's because this droplet was moving much, much faster than the droplets that were that formed the stains with these single tails. So one possible application of tails is to use it when it comes to our stain selection criteria and help us to find those stains that are moving the fastest, which are going to be affected by drag the least. The reason why that's important is as we find stains that are affected by drag less and less, that is going to get our height component closer and closer to the actual area, the actual height. The more stain is affected by gravity and drag, the more it raises the area of raises the height component of that area of convergence and area of origin calculation. So that's one application. Another potential application it comes to pattern classification. So here we have two patterns that are on a vertical surface. We got pattern L that is on the left-hand side. We have pattern M that's on the right-hand side. Both of these patterns are elliptical to slightly circular shaped distributions of stains. But we're going to look at L, and I want us to focus on the tails. And as we look at the tails of these stains, all of these tails are single tails. We don't have any jagged shaped tails. They're all downward moving stains, so this means we're not really going to be able to do an area of convergence or area of origin calculation for this because we are way going to overestimate our height. But when it comes to classification, these single tails that are extending from these spatter stains give us an indication of how fast these particular droplets were moving at the time of impact. That relatively speaking, they're not moving particularly fast because they were only formed a single tail. However, if we move over to pattern M, we've got a collection of elliptical shaped stains. And as we look at this, there's a lot of fascinating features with this particular pattern. But if we look at the directionality, these stains are not moving downward. These stains have more of a left to right directionality to them. The larger stains actually have pooling of blood. This is in the lower half of those. But again, let's focus within on the tails. And we're going to zoom in, and as we look at some of these tails, particularly the ones in the centers, we're going to see that the tails are not single tails that are coming off, but the back sides of these actually have indication of streaks and splashes that are coming. So this is going to tell us that these particular droplets were moving much faster when they hit the target surface than the droplets that created pattern L. Now, that's going to help us when it comes to classification because we're going to look at what mechanisms that are going to create fast-moving droplets and other mechanisms that are going to create slower-moving droplets. Both of these are going to be spatter-producing events. So pattern L with the downward-moving droplets those are satellite stains from a drip pattern, and pattern M that we're looking at in this particular image are spatter stains from an impact pattern. So you may not be able to come to that conclusion based on the limited information that we've provided you so far, but a drip pattern is a relatively low energy event, whereas an impact pattern is a relatively high energy event, and that the differences in those energies is going to be seen within the tails. So I hope you enjoyed this. It's a different look at some of the features of spatter stains, and hopefully it'll encourage you to pay a little more attention to the tails as you're doing your evaluation. Encourage you to please keep watching for other videos as I add them to the series. And as always, if you have any questions or concerns, please reach out to me. The email address is down at the bottom.